Welcome! In this video we are going to talk about the usage of mixtures with several inert gases and its impact in ZHL16 decompression algorithm. We will see why we use such mixtures with inert gases other than nitrogen and how we can adjust ZHL with Graham's law of diffusion to calculate decompression with such mixtures. Finally, we will see the limitations of theoretical models when compared to actual experimental data. Warning: this video is for educational purposes only. The dive profiles shown in here were made entirely with theoretical models, most of the time known to be harmful to divers. Do not use these profiles in real dives. We see previously how we can use Haldane and Schreiner equation to track the amount of gas a diver absorb and expel throughout time. In this video we will use a slight variation of the gas profile graph. The yellow bar is still used to track the ambient pressure. The solid bar is used to track the pressure of inert gas dissolved in the tissue, and the pressure of several other inert gases dissolved in the tissue. The maximum ceiling of a diver will be given by the striped bar. As we have seen in previous videos, we use Professor Buhlmann A and B coefficients to track the maximum allowed ambient pressure for a given tissue pressure of inert gas. One thing we haven't discussed so far is the narcotic effects that nitrogen have in the body. A mixture of 79% nitrogen is narcotic starting from about 30 meters on. This means that a diver will gradually start feeling drowsy and lost its cognitive abilities, like been drunk. At about 100 meters, the vast majority of the divers would completely black out, pretty much drowning. I have no data of divers successfully been done for depths greater than 130 meters on air. Other gases like helium presents no such narcotic problem at those depths. And although helium presents its own problems, like high-pressure nervous syndrome, we will not discuss them right now. We saw previously that we can simulate our body with several different tissues, each with a given half-time. The half-time is the time for a tissue get half-saturated. Professor Buhlmann used this half-times to calculate A and B coefficients. Although A and B coefficients were calculated for usage with nitrogen, there is nothing in its definition directly linking it to this specific gas. A and B depends only on the half-time of the tissue. We know that each tissue will absorb and expel gas at different rates for different gases. The faster a tissue exchanges gas, the shorter its half-time will be. The coefficients are calculated based on the tissue half-time. For mixtures with another inert gas composition, we will need to know the half-time for those tissues with that specific inert gas. If we have a way to calculate the half-time of this tissue for another inert gas in relation to nitrogen, we will have all the necessary information. With this new half-times in hand, we can easily compute the coefficients with A and B formula for this new inert gas mixture. But how do we calculate the relation of a tissue's nitrogen half-time to another inert gas half-time? We can simply use Graham's law of diffusion. Graham's law of diffusion was formulated by Thomas Graham in 1848. His law states that the rates at which different gases diffuse are inversely proportional to the square root of their molar masses, where A1 and A2 are the rates that the gases 1 and 2 diffuses, and M1 and M2 are the molar masses of the gases 1 and 2 in unities of weight per mole. The rate of diffusion is inversely proportional to the tissue half-time, so, for our purpose, Graham's law can be rewritten in terms of half-time. Given that the coefficients were originally derived for nitrogen, we need to know the molar mass of nitrogen and the molar mass of the other inert gas that we want to compare to nitrogen. We already know the tissue half-time for nitrogen. We can find the tissue half-time for this other gas and therefore know the A and B coefficients for this gas. Let's see an example where we calculate A and B coefficients for the fastest helium tissue within ZHL. The fast ZHL16 tissue for nitrogen is 5 minutes. The molar mass of molecular nitrogen is 28.02 grams per mole. Remember, nitrogen forms a molecule of 2 atoms, so its molar mass is twice of atomic nitrogen. Helium is a noble gas and forms no molecule under normal conditions. The molar mass of helium is 4.0026 grams per mole. We can use the previous formula to calculate the helium half-time for the nitrogen 5 minutes tissue. Substituting those values, we can calculate the rate between the half-time of nitrogen and helium. This value is the diffusion rate of helium in relation to nitrogen, or simply diffusion rate of helium. For the 5 minutes nitrogen tissue, the equivalent half-time for helium will be approximately 1.88. We can use the formula for the A coefficient to calculate the helium coefficient for the 1.88 half-time. The same way, we use the formula for the B coefficient to calculate the helium coefficient for the 1.88 half-time. We have just calculated the helium equivalent for 5 minutes half-time. Now, we can use this logic to calculate the half-time for all helium tissues. With those values of half-time, we can easily compute the coefficients for helium in all 16 tissues of ZHL. Now it is easy to calculate a dive table with heliox, which is a mixture with helium and oxygen. First, we assume that the diver is saturated with our heliox mixture at surface level. Let's see an example for a dive with a 50% mixture of heliox at 50 meters for 40 minutes. Note that the tissues half-time used are the ones for helium. The descent of the dive is calculated as usual with Schreiner equation. In the bottom, we can use Haldane equation to track the amount of inert gas absorbed. We use the coefficients calculated for helium to find the ceilings of this dive. Let's compare this heliox dive with a dive done with air. The dive with air is calculated as usual. It seems that we can use this method to calculate the dive profile of any mixture of oxygen and one inert gas. But there are some major caveats, as we will see later in this video. We can see that the dive profiles are too different to be true, but let's not get ahead of ourselves. But the question we will address first is, how to calculate decompression for mixtures with several inert gases. The most common mixture with several inert gases is trimix. Trimix is a mixture of helium, nitrogen, and oxygen. Usually trimix is labeled with TX followed by the oxygen content and helium content. This example is a mixture with 18% of oxygen and 35% of helium. For each tissue, we need to calculate the absorption for each inert gas separately. So for trimix, we need to track the amount of absorbed nitrogen and also helium, both separately according to their half-time. But how do we calculate the ceilings for this combination of gases? The max pressure allowed in the tissue and the coefficients A and B have a linear relationship, where the max pressure is the ceiling for this tissue. This means we can calculate the ceiling using a linear combination of A and B coefficients for all inert gases used in the mixture. We can do that with a weighted mean between all gases, where the weight we use is the amount of partial pressure of each inert gas. In the example, the A and B coefficients are calculated as shown. This means that at any moment in the dive, a new value of A and B have to be calculated, since the amount of inert gas is always changing according to the partial pressure of those gases dissolved in the tissue. Let's consider an example of a dive with a mixture of trimix 1835, meaning a mixture of 18% of oxygen and 35% of helium, for a dive at 50 meters for 40 minutes. The dive starts as usual, calculating the absorption of each inert gas according to Haldane and Schreiner equations. When the diver starts to ascend, the ceiling is calculated using the weighted A and B coefficients according to the dissolved amount of helium and nitrogen. We keep the same procedure as before. The difference is that a new value of A and B have to be calculated each step. Of course, we can use enriched mixtures as seen previously to accelerate decompression. In this case, let's use nitrox 50 and oxygen to accelerate decompression. We can use the same logic to calculate a dive with trimix and several other decompression gases. The dive starts as usual. The diver ascends to the 22 meters decompression stop, where a mixture of nitrox 50 can be used. The diver switches mixtures and proceeds with decompression. When the 6 meters is reached, which is the maximum operational depth for oxygen, the diver switches mixtures again and finishes the dive. Notice that since the decompression was done with nitrox, the total amount of dissolved helium in the tissues is way lower than before. With this procedure in mind, we can calculate a diver decompression for any mixture of inert gas. Let's see an example of a diver using a mixture of the following inert gases: 20% nitrogen, 20% helium, 20% hydrogen, 20% radon, and the left 20% top off with oxygen, making this the first pentox gas mixture profile that I'm aware of. First, we get all molar masses of those gases and calculate the ratio between the half-time of the gas and nitrogen. We use this value to calculate the A and the B coefficients for each gas. The final A and B coefficients are calculated as the weighted mean between all gases. Now we can start the dive. The diver starts saturated at sea level with air and will have the same profile as before, 50 meters with 40 minutes bottom time. As the dive progresses, the divers start to absorb other inert gases. Take a notice that the heavier the gas, the more difficult it is for it to be absorbed or expelled. In this case, radon is the least absorbed gas. We use the partial pressure of each inert gas to calculate the A and B coefficient used to track the ceiling. As the diver ascends, the inert gas is expelled. Once more, radon was the less expelled gas, due to its high molar mass. All of this are very beautiful, but as we said before, there are caveats. Major caveats, as a matter of fact. In his book Diving Medicine, Professor Buhlmann never extrapolate the helium A and B coefficients from the formula for nitrogen. Those coefficients were calculated experimentally, and no formula was provided. Even for nitrogen, Professor Buhlmann provided other sets of coefficients that were corrected and considered safer than the theoretical ones. So, don't use this formula for anything other than educational purpose only. Using this formula can be considered an educated guess at best. In the worst case, it is probably completely wrong. Any coefficient for any type of gas must be tested with actual experimental dives under controlled circumstances. So, don't use this. Finally, ZHL model do not tackle other issues caused by inert gas, like narcosis, high-pressure nervous syndrome, hallucinations, and biological interaction with those inert gases. In this particular case, there is a tiny bit of a problem with radon. Radon is a carcinogenic gas. No person in its right state of mind should purposely inhale radon. But we know that this wouldn't stop the most hardcore technical divers among you. But how much the theoretical model differs from the experimental one? Let's analyze two scenarios to highlight those differences. The first one is a short but deep dive of 60 meters for 5 minutes. This will be the model with the coefficients for helium and nitrogen that Professor Buhlmann corrected experimentally. We are using only helium and nitrogen because we do not have those coefficients form hydrogen, and definitely we do not have coefficients experimentally obtained for radon. The second dive is done with the values for the theoretical coefficients form the A and the B formulas of Professor Buhlmann as shown previously. As we already know, deep and short dives are bounded by the faster tissues. We calculate those dives as usual. After the dive finishes, we can clearly see that the experimental coefficients are more conservative with the fastest tissues. We end up with deeper stops. This means that the theoretical model is not safe enough for the fastest tissues. And since high gradient pressure in fast tissues are linked to DCS type 2, the theoretical model can lead to serious health problems. The second dive is a relatively shallow but long dive. It is a 30 meters for 2 hours dive. Once more, this is the experimental one, and this the theoretical one. The dives go as usual. This time the dive is bounded by the slowest tissues. We can see that now the theoretical model imposes a much larger penalty for shallow stops. This penalty makes the dive longer with no need. And this is why we said that the ZHL theoretical coefficients are not conservative enough for fast tissues and too conservative for slow ones. That's it for today. We hope you have enjoyed and learned something useful. Next video we will talk a little bit about gradient factors and how it is used with decompression algorithms. See you next time, and safe dives for us all.